Hi everyone, we've made it to kind of our lecture on vector components. So let's take a look. Let's keep on going back to this narrative. It says a motion of an object can be described in terms of displacement, velocity, and acceleration. And before we can do that, we have to get into vector components. And each one of those, displacement, velocity, and acceleration, can be kind of described by vector components. Let's start with a quick definition of a vector. A vector is any kind of measure that has a magnitude and a direction. The magnitude describes how much, and the direction describes kind of where is it going. So if we talk about notation real quick, we kind of have the A with the arrow. That kind of is just our vector notation, meaning that it has a direction. And if we kind of put it between these pair of parallel lines, that means it's just the magnitude of the vector. It's not going to include the direction, just how much. So quickly, let's draw a pink vector, and this is kind of our kind of big velocity, and we're going to split it into kind of two components, kind of a y direction and an x direction, and each one of those are going to be kind of vector components. So x and y are vector components of kind of the big V. Simple enough. Let's go ahead and kind of write some formulas for Vy and Vx. It's kind of, they're straight out of trigonometry, and we all kind of have these memorized. So let's just kind of do it quickly. Vy is V sine theta. And then Vx is going to be V cosine theta. Very cool. So you kind of have to define the theta, and the theta is kind of the elevation off of the x-axis, and you just kind of use SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent. So the next question we have to ask ourselves is, when are we going to use vector components, especially kind of with respect to living systems? Because that's what all 4A is about, and that's kind of the major selling point of these videos. So let's take a look. Whenever you have a resultant, maybe it's an external force, or maybe it's kind of the net force. You're already taking all the nets, and you kind of want to do the opposite. You want to split that net force into its components. You need to break it into its components, and after breaking it into its components, you can come up with kind of very interesting physics, and that physics can help you kind of come to certain conclusions about living systems. So it will allow us to predict the behavior of living systems. Okay, let's go ahead and take kind of a quick example. So for example, you could have kind of a shoulder, and this shoulder only dislocates if you have a certain kind of downward force on it. Fy has to be at least 15 newtons downwards for the force for the shoulder to dislocate. Well, kind of what kind of force net or what force external could you kind of put on a shoulder to have it kind of not dislocate, or to have it dislocate? And you're going to have different thetas. So different thetas will give you different Fy's. We kind of saw that from the last kind of Fy equals F times sine theta. Or you might have kind of a migrating population. This population is kind of migrating maybe in like a northeast direction, and that's kind of their velocity. And you kind of know when will they reach a certain latitude, or when will they reach a certain longitude. To know that, you kind of need to know the y component of their velocity, or the x component of their velocity, and through that you can kind of have a better understanding of how far they're going in the x direction or y direction. So next, let's talk kind of about something else that we can do with components, and that's kind of, it can help us understand the physics behind certain kind of translational motion topics. And I'm going to cover kind of 3 examples real quick. The first example is frictional forces, and we all kind of have had some introduction to frictional forces. We know that's very dependent on Fn, the normal force, and the normal force can sometimes be straight downwards, or if you're on an incline, normal force kind of changes. So we can go ahead and just kind of leave that in the back of our head somewhere, and we'll cover it soon. It could also depend on weight, and weight is kind of our force gravity. So if you had this kind of complex kind of F net, you might have to split the force gravity into its own component, and that can change a lot of our physics properties, kind of how much gravity. And then you have kind of projectile motion. And projectile motion is kind of really when we're going to take advantage of this kind of splitting things into components. If I draw kind of a small little cannon here, and you can see at every single moment inside this kind of cannonball's trajectory, there's never 2 moments where it has the same kind of vector components. There's going to be certain times where kind of its x component or its y component is going up, and its x component is going to the right, and then kind of later it's going to be x component going to the right and y component going down, and then kind of at the very tip might not have a y component at all. So maybe you're kind of asking by now, what do I need to know about kind of vector components? I have the idea that kind of what Vy and what Vx is, but let's go ahead and kind of just take a look at it with a little bit more detail and no extra detail, kind of exactly what you need to know for the MCAT. So if I have this kind of purple vector, it needs to have kind of a direction, so it's going kind of, you can call this northeast. I'm going to split it into kind of its y and x vectors. And what you kind of really need to know is when you're splitting a vector into its kind of components, you always go head to tail. So this is kind of something that it's brought up a lot in physics classes, and I think you've all heard of it before. So you kind of start at the tail of the original vector, and that kind of becomes your first tail of your x component, and then your y becomes its head, becomes right at the head of kind of your big component, and you just kind of do two kind of head to tails. Simple enough. So let me just go ahead and write that down. So kind of the tail of your resultant, so the tail of my kind of big V, becomes the tail of my first component, which is kind of Vx. And then Vx has to kind of have obviously a head on the opposite direction, and then kind of the head of my last component has to be right at the head of kind of my big V. And as long as I kind of keep on going head to tail, I should always be in good shape. Okay, I think it's time for us to solve an example, so let's go ahead and take a look at one. I just drew kind of my Vy in there. I'm drawing kind of my external force. And give it a downward. So let's give a question. So you need a Vy of at least 15 newtons downwards to kind of dislocate a shoulder. So that kind of, that little joint right there where the red line meets the blue line, that's going to be my shoulder joint. And I'm going to go ahead and ask if the shoulder is dislocated by a F of 30 newtons, what kind of theta would I need? Or what are the possible thetas that could kind of allow this shoulder to be dislocated? So kind of theta has to have at least be such that F of y is 15 newtons, but it could be more. 20 newtons would also dislocate the shoulder. So let's go ahead, kind of set it up, label our points. My Fy is going down. My 30 newtons is also kind of going in a southwest direction. And I can just say right off the bat, sine theta equals 15 over 30. If I want to write it kind of more traditionally, I can do that too. Kind of Vy equals V sine theta, and then solve for sine theta. But I can just look at the right triangle geometry, and I get that sine theta has to be kind of 1/2. I actually kind of know my special rights, my 30, 60, 90s, and my 45, 45, 90s. And hopefully we all know that kind of, that means that theta is 30 degrees. And I'm going to go ahead and say that's 30 degrees minimum. It's at least 30 degrees. It could be more than 30 degrees, and it would still dislocate. But you don't have to take my word for it. So let's go ahead and kind of try to prove it. If I take kind of a quick graph of sine theta, that's kind of the sinusoidal graph, and right there is kind of 90, where it reaches its maximum. And I'm going to go ahead and plug in 30. Right there around 30, that's 1/2. So it's very clear that kind of anywhere between 30 and 90, sine theta is only getting bigger. So if sine 30 will do the trick, then anything kind of between 30 and 90 will definitely do the trick. So kind of sine is increasing from sine 30 to sine 90. And you can kind of try that out in your calculator. So I would say the minimum you can need is kind of 30 degrees. Or it could even be more. Obviously, if it was kind of 90 degrees and it was all acting downwards, that would kind of give you a Vy of 30, and that would definitely dislocate the shoulder. So the last topic that we have to talk about is, do we always have to kind of be breaking things down into kind of x and y components? And then kind of the clear answer is nope. So let's go ahead and kind of take a quick example where we can break down any kind of resultant into any other two vectors. So I'm going to make this kind of first pink vector, and they no longer have this kind of right angle. It's not that one of them is x and one of them is y, it's just kind of two vectors, and one of these could be kind of like your forearm, the other one could be kind of your upper arm, and the resultant could be kind of the force traveling through your total arm. But you can see here that it kind of A plus B equals C, and you keep on this head to tail kind of naming convention, and kind of goes from B to A, and then B plus A gives you completely R. So kind of what now? How could I find kind of what A is or what B is? How could I break this down? And you have to kind of use the law of cosines. It's something that's good to kind of have in your bag of tricks, but you don't have to have it kind of completely mastered for the MCAT. But it's kind of good to know that you don't always have to break things down into X and Y components. You can break down a vector into kind of any two components and make any angle with each other. Let's just quickly kind of go over the law of cosines. R squared equals A squared plus B squared minus 2AB cosine R, where R is kind of the angle across from kind of the R vector. Simple enough. If you were solving for A, you could kind of rearrange this formula to solve for A and kind of bring everything over and kind of isolate A, and you could say kind of R squared minus B squared plus 2AB cosine R kind of equals A squared. That's completely allowed. You can even set up the whole entire equation to kind of be kind of A squared equals. I could say A squared equals B squared plus R squared minus 2BR cosine A. So it's kind of just the same thing as kind of the equation that's kind of in the light green, but now I'm solving for kind of A squared. And the nice thing about law of cosines, unlike the Pythagorean theorem, is you can have it kind of solve for any of the sides. You don't have to kind of worry about C squared always being the hypotenuse and A squared plus B squared equals C squared. So either way, just kind of have this in your bag of tricks. You won't need to kind of do it on the MCAT, but it's good to know that you can break down a vector into any two components. So that's everything you need to know about vector components for kind of the new MCAT. Please like and subscribe for more videos.